Let's start with the week 4, in which we are going to discuss different sorting algorithms in detail. So, what is sorting basically? So, sorting is arranging the elements in a particular sequence, like you are arranging them in ascending order or descending order. Sorting is one of the very fundamental concept of computer science. We use it as a subroutine, as a function, built-in function in various programming languages like Python, Java. So sorting is in which we are arranging the elements in ascending order or descending order, or we can say in increasing order or non-decreasing order. Okay, so we have sorting of two types. One is the internal sorting and one is the external sorting. When all of our data is in the main memory, which is called as RAM, random access memory, then we perform the internal sorting, that is called as internal sorting. But when our data is on external storage, like your hard disk drive, and so that is called as external sorting. Also, we categorize sorting by two ways. One is the comparison based and one is the non-comparison based. Comparison based sorting, in which we perform the sorting by comparing two elements, whereas non-comparison sorting, in which we compare two elements based on their size. For example, the number of digits in a number, like 10 has 2 digits, 100 has 3 digits. So obviously 100 is going to be bigger than 10. So we count the number of digits in a number and accordingly we compare the numbers. We'll discuss about this later on. So as we said, internal sorting versus external sorting. So whenever data can fit entirely in the main memory, then we perform the internal sorting. This is basically relevant for small to medium sized data which can fit in the main memory. The examples include your bubble sort, quick sort, merge sort, heap sort, and all. Whereas external sorting, when data is large enough and it cannot fit in the RAM, as all of us know that RAM is limited in size. So in that case, our data is resides, the data is stored on the hard disk, and then we need to perform some of the input output operations, some of the disk based input output techniques to read out the data to sort them. So that is done as external sorting. For example, external merge sort. Now make sure merge sort can be performed by both ways, internal sorting as well as external sorting. Okay, the next concept, the next quality, basically I'll say the next feature of sorting is as stable versus unstable sorting. When the relative order of equal elements is preserved, when the relative order of equal elements is preserved, we call it as a stable sorting. It is generally useful when we are having the objects based on the multiple keys, like your object is having an employee ID, employee name, his address, contact number, multiple keys. So in that case, if we're comparing, for example, employee ID, so employee name is preserved. The sequence of employee name is preserved if the names are same. So that is called as stable sorting. Bubble sort, insertion sort, merge sort, counting, radix sort, all these are stable sort by default because in these relative order of elements does not change, equal elements. On the other hand, if relative order of equal elements may change, then we call it as unstable sorting. Quick sort, heap sort, merge sort, these are the examples of, selection sort, these are the examples of unstable sorting. Comparison based versus non-comparison based sorting. As we said, the comparison based sorting is done by comparing the elements, like 10 is less than 11, 11 is less than 12, or alpha is less than beta, right? So these, when we're comparing the elements based on the which element is smaller, which element is greater, that is called as comparison sorting. The lower bound for these ones basically is big O of n log n. For example, bubble sort, insertion sort, selection sort, all these are examples of comparison based sorting. In non-comparison based sorting, we sort elements using their properties. Like we said, the number of digits. Like again, like 10 has 2 digits, 100 has 3 digits. So 100 is bigger than 100 is greater than 10. So we based on the number of digits we count. Then number of inversions. The number of inversions is the inversion basically is when index of element like I is less than j, index I is less than j, but element is greater than j. For example, here if you see the indexes are 0, 1, 2, 3, 4. Index 0 is less than index 1, but element 5 is greater than 4. So this is called as inversion. That means when elements are not in correct order, that is called as inversion. So how many inversions are there? For I equals to 0, if you see 5 4 is an inversion, 5 1 is an inversion, 5 2 is an inversion, and 5 3 is an inversion. So from 0 to 4 there are 4 inversions. Then if you see from index 1, that is element 4, so 4 1 is an inversion, 4 2 is an inversion, 4 3 is an inversion. So there are 3 inversions. Then if you see with element 1, 1 2 is not an inversion because 1 is less than 2. 1 3 is not an inversion. Then if you check with element 2, so 2 is less than 3, so it is not an inversion. Okay, and at element 4 the loop terminates, the condition terminates because there is no other element after element 3. So how many total inversions you have here? 4 plus 3, which comes out as to be 7. So there are total 7 inversions. We need to check out how many, why it is important physically, we need to check how many inversions are there. So accordingly we need to perform the number of swaps to arrange the elements in a particular ascending or descending order. Now let's first discuss our bubble sort algorithm. Bubble sort is one of the simplest sorting algorithm. How it performs basically, it repeatedly swaps adjacent elements if they are not in the correct order. So we say we bubble up the elements. It is an internal sorting, comparison based sorting. The time complexity is in best case. The best case time complexity means the elements are already sorted. Like elements are 1, 2, 3. These are already sorted. So this is the best case. In the best case, the complexity is big O of n. The worst case, for examples, the element are 3, 2, 1 and I want to arrange them in ascending order. So it is the worst case because we need to perform maximum swappings, maximum comparisons. And average case, when it is some elements are in ascending, some elements are descending order, then the average case, so average case complexity is big O of n square again. It's an in-place algorithm, that means it does not require any additional memory for performing the sorting. So the space complexity is big O of 1. It is a stable sorting algorithm. Now let's see how does it work. For example, we are having the elements 5, 1, 4, 2, 3. So in case of first pass, 5 is compared with 1. The elements are not in correct order, so we will swap them. So these two elements will be swapped. So 1 will be here, 5 will be here. Now 5 and 4 will be compared. Again, these elements are not in correct order, so these will be swapped. So 4 and 5. Now 5 and 2 will be compared. Again, these are not in correct order, so these will be swapped. So 2 and 5. Now 5 and 8 will be compared. Since the elements are in correct sequence, so there no swapping will be there. So after first pass, your elements will be 1, 4, 2, 5, 8. Now make sure after every pass in bubble sort, the largest element goes on its place. Like the largest element of this array is 8. So after first pass, 8 will be at its last position. Then in the second pass, the second largest element, which is 5. So that will be on its position. After third pass, the third greatest element, which is 4. So 4 will be on its position. In this way it works. This is the algorithm for a bubble sort to arrange the elements in ascending order. It is basically done by a nested loop because we need to compare every pair of elements, and we compare the elements. If elements are not in correct sequence, we swap the elements. Let's say one more example. Let's say the elements are 5, 3, 4, 1. So in pass 1, 5 and 3 will be compared. These are not in correct order, so it will be 3, 5. Then 5 and 4 will be compared, not in correct sequence, so it will be 4 and 5. We swap them. Then element 5, 1 will be compared, not in the correct sequence, so 1 we will swap them, so it will become 1, 5. So 5, the largest element, is at the end of the array. Then in the second pass, so we have this array for the second pass. Now 3, 4 will be compared in the correct sequence, so no swapping will be there. Then 4, 1 will be compared, not in the correct sequence, so these will be swapped. Then in pass 3, 1, 3 will be compared, not in the correct sequence, so swapping will be there, so it will become 1, 3, 4, 5. Now 3, 4 will be compared in the correct sequence, so no swapping. So the finally sorted array is 1, 3, 4, 5. The next algorithm is the insertion sort algorithm. Insertion sort algorithm is based on the concept that take one element in the array at a time and put it at its correct position in the array. And we always assume that first element is correctly sorted in the array. It is internal comparison based sorting. The best case is big O of n. Average case and worst case complexities again big O of n square. It is an in place stable algorithm. This is the algorithm, how it works. Now, again, let's say we are having the elements 5, 3, 4, 1. As we said, that we always assume that first element is on its correct position. So our elements are 5, 3, 4, 1. Then we start with element 3 and always check towards the left of the element. So 3 is, if you compare 3 with 5, 3 should be before 5. You compare 3 with 5. So what we are going to do, we will shift 5 over here. So it will become 5, 5, 4, 1 and then put 3 on its correct position. So it becomes 3, 5, 4, 1 after first pass. Then after second pass, we need to check element 4, which is at index 2. This is index 1, this is index 2. So at index 2, now 4 will be compared with 5. 4 is smaller than 5, so 5 will be copied here. So it will become 3, 5, 5, 1. Now 4 will be compared with 3. Since 4 is greater than 3, that means the correct position for element 4 is this. So 4 will be put here. So it will become 3, 4, 5, 1. Now with element at index 3, which is 1 in the next pass. So 1 is compared with 5. So 5 will be copied here because 1 is smaller than 5. Then 1 is compared with 4. Again, since 1 is less than 4, so 4 will be shifted here. Then 1 will be compared with 3. Again, 3 is greater than 1. So 3 will be copied here, or we can say shifted here, and then 1. 1 will be put at the beginning of the list. So it is the final list, sorted list. We are performing all the algorithms for ascending order in increasing order. The same algorithms can be implemented for non-increasing order just by reversing the condition. Then selection sort. Selection sort is take the minimum element. Take the minimum element of the unsorted portion and swap it with the first element of the unsorted portion. I'll let you know how does it work basically. So again, it is an internal sorting comparison based. Complexity is n square, n square, n square. Since it is an in-place sorting algorithm, so the space complexity is big of 1. It is unstable. It is not stable because equal elements may change their relative order. This is the algorithm for selection sort. How we perform it actually. So let's say again we are having the elements 5, 3, 4, 1. Now find minimum element in the array. So minimum element is 1. So swap it with the first element. So it becomes 1, 3, 4, 5. So this is your sorted array. This is your unsorted array. Now you have to perform operations always in the unsorted array. Now again find out the minimum element in the unsorted array. This is 3. It should be the first element. So swap it with itself. So 3 becomes here. So now 1 and 3 becomes sorted array. 4 and 5 becomes unsorted. Again from 4 and 5 find out the minimum element, which is 4. Swap it with the first element of unsorted array. So that means it will be swapped with itself. So 1, 3, 4 becomes the sorted array and 5 becomes the unsorted. Now since it is the single element, so the process ends. So your sorted array becomes 1, 3, 4, 5. So in bubble sort, we compare adjacent elements and we swap if they are not in correct order. In insertion sort, we take one element at a time and put it on its correct position. And in selection sort, we find out the minimum element of the unsorted array and swap it with the first element of unsorted array. I'll advise you to implement all of these algorithms in C++. Now, the lower bound for simple sorting algorithms. This bubble sort, insertion sort, selection sort, all these are considered as simple sorting algorithms. And any algorithm that sorts by swapping only adjacent elements requires at least proportional to n square time on average. You have seen on all of the three algorithms, the average case complexity is big O of n square. Because the reason is that every swap, in every swap, we are removing at least one inversion, right? So an observation says that an average number of inversions in a random array of size n is approximately n times n minus 1 divided by 4, which grows on the order of n square. So to achieve a faster sorting than big O of n square, because big O of n square is not a good time. So an algorithm must be able to swap elements which are far apart, not the adjacent ones. So we use shell sort algorithm in which we compare the elements which are at a distance. We do not compare the element, we do not compare the adjacent elements. We compare the elements which are far apart from each other. So we maintain a variable gap here, and every time we reduce the value of gap to half until it becomes 1. It is an internal comparison based sorting. The time complexity is big O of n log n, the best case. Average case is n raised to the power 4 over 3, and generally depends upon the value of gap, that which gap we are taking. And worst case time complexity is again n square. It is space complexity is big O of 1. Stability, it is unstable. Now, how does it work basically? Let's say we are having the elements 5, 4, 1, 2, 3. The initial value of gap we are taking as 2. It depends upon you that what value of gap we would like to take. Here we are taking the gap value of 2. What does it mean? We will compare the elements which are at distance to. That means we will compare the elements 5 and 1. We will compare the elements 4 and 2. And then we will compare the elements 1 and 3. And we will swap if they are not in correct order. So if we compare elements 5 and 1, that is the first one, they are not in correct sequence, so we will swap them. Then we will compare 4 and 2. These are not in correct sequence, so we will swap them. Then we will compare 5 and 3 since it goes by index, not by value. So you are going to compare by index. So the elements are not in correct order. 5 and 3 are not in correct order, so we swap them. Then in next step, we take the gap of 1. That means we are performing the normal insertion sort algorithm. Since our elements are already sorted, now in this case, so it is already sorted, no swapping has to be done. So if you see here in this array, by using the shell algorithm, we just needed to perform only 3 swap and our sorting is done. So less number of swappings are done. So it reduces inversions faster than simple insertion sort. Because in simple insertion sort, we need to perform multiple comparisons, but here we need to perform very less comparisons. Efficiency depends upon the gap sequence, that what is the value of gap you are taking. It is unstable because swapping distant elements may change the relative order of equal elements. Then comes the heap sort algorithm. We have covered the heaps in the last week, and we know that we are having two types of heap, max heap and min heap. Max heap, the concept is simple of performing the heap sort. Take out the root element and put it at the end of the array. Perform the heapify operation to make your heap, to make the heap property. Then again extract the root element, put it at the end of the array, and he performed the heapify operation to maintain the heap property. And in that way, you will have the sorted elements with you. Again, it is an internal sorting algorithm, comparison based. The time complexity here is very less. It is big of n log n, n log n, n log n. It is an in place and unstable sorting algorithms. So, how we perform? I am not covering the algorithms at this time because I want all of you to implement these algorithms yourself. If you have any issues, just let me know. So, what we can do? The first we build a max heap from the array. Swap the root element because the root, if it have the max heap, then root will have the largest element. So swap the root element with the last element. Reduce the heap size by 1, then heapify the root to maintain the max heap property. Repeat until all elements are extracted. So this is basically the pseudocode. So let's say 5341. If you create a heap, it will be 5, 3, 4, and then 1. Now we need to perform the heapify. So swap 5 and 1. So 5 will come here, 1 will come here. Now it is not here, right? Because we are reducing the heap size by 1 every time. Now, if we need to maintain the heap property, we will compare 1 with 3 and 4. Since 4 is greater, so 4 will come here and 1 will come here, right? So your heap becomes after first step 4, 3, 1, and then 5. Now your heap is 4, 3, 1. So now extract the element 4. So 4 will be swapped with element 1 because this is the minimal one. So 4 here, 1 here. Now out of 1 and 3, we reduce the heap size by 1. That means the heap size is now 2. So out of 1 and 3, heap property will be 3, 1, 4 and 5. Now extract 3, so swap 3 with 1. So 3 will come here, 1 will come here. 1 is the only element. So now if you take the element, you are having the sorted element 1, 3, 4, 5. Heap sort is always big O of n log n, whether it is best case, worst case or average case. It is in place but unstable, very efficient for large data sets. Then we perform the merge sort. Merge sort and quick sort are based on divide and conquer strategy, and merge sort is a comparison based sorting algorithm. So divide and conquer strategy is divide all of your array elements, split your array into half until each sub-array has size of 1. It is a recursive process. You need to recursively split your array into half until each sub-array has one element. Then perform the merge operation to merge all the elements back into a sorted array. It is an internal, or sometimes we can use it as an external sorting algorithm also. It is comparison based. Best case, worst case, average case is again big O of n log n. Space complexity is big O of n. It is not an in-place sorting algorithm. It requires auxiliary array, some temporary array for the merging operation. But it is a stable sorting algorithm. No. So we have two functions here. One is merge sort and one is the merge. Merge sort, these two are used for splitting the array into half recursively. This one is for the left half, this one is for the right half, and this is for the left half and this is for the right half. And once all of your areas is splitted, then you call the merge function to merge the elements. So split method is divide the array into two halves recursively until single element arrays, then perform the merge operation to merge two halves and merge them in sorted order. Repeat until the whole array is sorted. Like we're having the element 5, 3, 4, 1. So if we split it 5, 3, 4, 1, it will be split it in two parts. One part will be 5, 3, another part will be 4, 1. Then we again split it, so it will be 5, 3 because the array of in split it in half, then it will be 4 and 1. Now since each sub-array has size of 1, it cannot be further splitted. So we start to merging them. So now start merging them in terms of sorted array. So 5 and 3 will be merged. It will become 3, 5. 1 and 4 and 1 will be merged. It will become 1 and 4. Then we will merge 3, 5, 1, 4 and it will become 1, 3, 4, 5. You will get a sorted array. One more example, like we are having the element 6, 5, 12, 10, 9, 1. We split the array into halves. So first array got 6, 5, 12, second got 10, 9, 1. Then we perform the recursive splitting. So one element 6 and 5 and 12. Then one element 10, 9 and 1. 6 is a single element, so it cannot be splitted further. 5 and 12 can be splitted in 5 and 12. Then 9 and 1 can be splitted in 9 and 1. Now we start merging them. Since all the elements has size 1, so we start merging them. 5 and 12, if we merge them in sorted order, it will be 5, 12. 9 and 1, if we merge them in sorted order, it will be 1 and 9. Now 6, 5 and 12 will merge as 5, 6, 12 here. 10, 1, 9 will merge as 1, 9, 10. And if we merge these both, it will become 1, 5, 6, 9, 10, 12. Merge sort is one of the most efficient algorithm. But the problem with merge sort is it requires extra memory for merging. And one more benefit of merge sort is that it can be used for external sorting also. Then let's talk about the quicksort algorithm. Again, it is based on divide and conquer strategy, and it is a comparison based algorithm. Divide and conquer strategy: divide your array into two halves and then perform the operation. So it is also a recursive algorithm like the merge sort. It works by selecting a pivot element from the array and partition your array according to the pivot element, such that all the elements which are less than the pivot should be on the left hand side and the elements which are greater than pivot should be on the right hand side. Quicksort is usually faster, unlike other algorithms, and it is really efficient. It is very fast due to the good cache performance. Okay. Okay. For example, how the quicksort work. Let's say we are having the elements with us 6, 3, 5, 1, 2. Let's say, and we chose mm, right, we chose 2, that is the last element of an array, as our pivot element. So 2 is considered as the pivot element. So we will perform the partitioning such that elements which are less than 2 are on its left hand side and the elements which are greater than 2 are on its right hand side. So 1 is less than 2, so 1 will be on the left hand side of 2, and 6, 3, 5 are greater than 2, so those will be on the right hand side. So now we are having two subarrays. One is 1, one is 6, 3, 5. 2 is on its position. Now we perform the same process for the left array and right subarray. If we perform the same operation for the left subarray, so 1, it is the single element, which means it is already sorted. Now let's go towards the right subelement. So again we need to choose a pivot element. So let's say again we will take the last element is the pivot. So let's say 5 is our pivot element. So 1 and 2 are already sorted. Now we talk. So in case of this subarray, we need to partition is such that all the elements which are less than this pivot are towards the left of 5 and the elements which are greater than 5 are on the right hand side. Now there are again two subarrays 3 and 6. Since both of these has the size of 1, which means the array is sorted. The choosing, look, we can choose pivot element any of the element. We can choose the pivot as the last element. We can choose first element of the array as the pivot element. We can choose middle element of array as the pivot element. It depends. So the pivot choice is critical. If we take the first element as the pivot element, the worst case of big of n square, because if the array is already sorted or reverse order, sorted in reverse order, so in that case the complexity will be big of n square. So what we do generally, either we take the last element or the same happens with the last element also. So what is the good approach is we take the median of three element, that is median of first, middle and last element. So it mitigates your worst case scenario. Partitioning the array. What is the strategy of partitioning? We also call it as Lomutu. So we take the pivot element, it is taking the high element as the pivot element, which means the last element as the pivot element, as we did in the previous example. Then index I tracks the position where all the elements of the left are less than pivot. So if element is less than pivot, swap it and swap pivot finally with the high element with the AI. It is an internal comparison based sorting. These are the, I think we covered it. Yes. And space complexity is big O of log n for recursive calls. Since it's a recursive algorithm, it requires some extra space for the recursive call stack. So it becomes big O of log n. It is an unstable sorting algorithm. This is the algorithm. So we first of all we call the partition algorithm, which partition our array, and then it's a recursive process. So again, for the left subarray, partition the same for the left subarray and for the right subarray. This is the algorithm for partition. So you need to select a pivot element. Generally we use as the last element. Compare the elements and partition the array such that elements which are less than equal to pivot go towards the left and elements which are greater than pivot go towards the right. Then place the pivot on its correct position. Recursively sort left and right subarrays. It is one of the most popular sorting algorithm. This is the example again 5341. We are taking pivot as one element, that is the last element. So you need to sort it array. You need to partition it. So element, there is no element which is less than 1. So there is nothing on the left hand side of the 1. But all the elements are greater than 1. So all elements will go towards the right hand side of 1. Then in the right subarray, you take the pivot element as the last element, which is 5. So you again partition it. So all the elements which are less than 5 should be on the left hand side and all the elements which are greater than 5 should be on the right hand side. And similarly we process it. Quicksort is very fast in practice, often outperforming merge sort due to its in-place operations. It is unstable, equal elements may change relative order. Pivot choice matters. As we discussed that we do not take first element generally as the pivot element, or you can take any random element also as the pivot element. So randomized or median of 3 pivot selection improves performance and avoids the worst case. It is always a good candidate for large data set and in-memory sorting. One more example is here, like suppose we are having the elements these. So we take 8 as the pivot element. So 8 is between. So all the elements which are less than pivot, that is 8, goes towards the left and all the elements which are greater than pivot goes towards the right. Then we perform the same operation for the left and right subarray. So the pivot, if we talk about the left subarray, 6 is the pivot. So all the elements which are less than 6 goes towards the left and all the elements which are greater than 6 goes towards the right. Same over here, the 12 is the pivot element. So all the elements which are less than 12 goes towards the left and all the elements which are greater than 12 goes towards the right. 6 and 7, 7 and 9 are the size is 1 of these subarrays. So process stops for these. For 2 and 1 again pivot is 1. So elements which are greater than 1 goes towards the right. For 15 and 20, 20 is the pivot. So elements which are less than 20 goes towards its left. So if you arrange these elements, if you check these elements in array, these are finally sorted. If you see it is 1, 2, 6, 7, 8, 9, 12, 15, 20. So the elements are sorted in the array. Now let's talk about some of the specialized sorting algorithms, which are basically non-comparison sorting algorithms. Till now we have discussed all the comparison sorting algorithms. These are now non-comparison sorting algorithms. Bucket sort is a distribution based sorting algorithm. So what we do in this case, we take number of buckets and we put the elements in those buckets according to some criteria, and then we sort each bucket individually. For example, this is the algorithm. Okay, let me just show you one example. Yes, this one. So let's say this is our array. We have created here 5 buckets. Bucket 1 consists of elements between the range 0 to 5. Bucket 2 consists of elements between range 5 to 10. Bucket 3 consists of elements between range 10 to 15, then 15 to 20, then 20 to 25. So all the elements which are in these range should be put in these buckets. Now sort these buckets individually. So you are, instead of large set, you are having smaller sets, multiple smaller sets. You can use any sorting algorithm like insertion sort to sort these internal buckets, then concatenate all these buckets to get the sorted elements. So distribute elements into buckets based on the value range, sort elements inside each bucket, then merge buckets sequentially to get the final sorted array. One more example is here. We are having suppose 5 buckets and my bucket index is floor value of n times value. So 0.25 times 5, it comes out to be 1.25. So the floor value becomes 1. That means in bucket 1, the element 0.25 will go. Same we calculate for all the values, that in which bucket which value will go. Then individually sort each bucket. So bucket 1 is sorted, bucket 2 is sorted, and then concatenate these buckets. It is efficient when input is uniformly distributed. Now, for example, in this case, your all the values are between the range 0 to 5 and one value is 20, which means the values are not uniformly arranged, distributed. So it does not work efficiently in this case. Performance depends on the number of buckets and distribution, that what is the number of how many buckets you are using and what distribution formula you are using. It can be implemented as a stable also if inner sorting preserves order, often used for floating point numbers or other limited ranges. Then another sorting algorithm, non-comparison sorting algorithm, is radix sort, in which we compare the elements based on these its least significant digits to the most significant digit. That means we start from the least significant digit and move towards the most significant digit. It is a stable sort. So how does it work? For example, we are having the array this one. Now we compare the elements of unit place, that is the least significant digit, and like for example this element is 045, this is 075, 090, because we are making the all the elements of the same length. So it becomes 002 and then 066. Now if we compare the elements based on the least significant digit, so it is 0 5 5 0 2 4 2 6. So put your element in the sequence of least significant digit. So it becomes 170, then 90, because the least significant digit. Then 802, then 2, then 24, 45, 75, 66. So if you see the elements based on the least significant digit are arranged. In the next step now, compare the element on their 10th place. Tens place. So that is 6 7 4 2 0 0 9 7 from this array and put the elements in according. So it becomes 802 2 24 45 66 170 75 90. Then in the third step, sort by the hundreds place. So you get these elements and finally you get the sorted array. So again, we are not comparing the elements, we are comparing their least significant digit to the most significant digit. If you see in this example again, these are the sum of the values original array First we compare based on least significant digit, then we move towards next digit, and then we move towards the hundreds digit. So finally we get the sorted array. It is a stable sort, so relative order of equal digits is preserved. It is efficient for large list of number with a small number of digits. It is not a comparison based sort, so we can achieve linear time for fixed size integers, and generally it is combined with counting sort as the internal stable sort. Now, all of these sorting algorithms were the internal sorting. That means where all the data were on the RAM we can read all the data at once. Now, external sorting, when your data is too large, it cannot fit into the RAM, so some of the data must reside on the disk. Like we use the hard disk or any of the external storage device. So sequential access is much faster there than the random access. So how we perform it? Load as much data as possible into the memory, then sort it internally like with quick sort or merge sort, then write the sorted chunk or run back to the disk. Repeat until all the data is sorted in runs. Then merge all the sorted runs into one larger run. So you will get all your sorted data. We can perform multi-way merge or polyphase merge. Simple merge, in which we merge two runs at a time, as we discussed earlier in the merge sort, where we merge only two sets at a time. In multi-way merge, we merge k runs simultaneously. It drastically reduces the number of passes needed, and but it requires big of k memory and a priority queue. Then polyphase merge, it is sophisticated merge strategy that balances basically your run lengths to minimize the amount of data processed, but it is more efficient than a simple multi-way merge. Then let's talk after this sorting algorithms. Let's talk about a disjoint set class. Disjoint set class we use whenever we need to maintain a collection of non-overlapping sets. Non-overlapping sets, to which we also call disjoint sets, when they do not have any element in common. Like all the values are distinct in both sets. There should be at least two sets, and in both of the sets there may be multiple sets, and each of the set on the values should be distinct. Like none of the two sets have common values. So there are two key operations we perform. One is the find operation, one is the union operation. Find operation returns the name of the set containing the element x, whereas union operation combines the set containing x and y. It is also called as union find data structure. We have multiple applications of union set, like in a minimum spanning tree, which we will discuss in the next week. Detecting cycles in the graph, again we will do it next week. Connected components in a graph. So general applications of disjoint sets are in the graphings, network topology and all. So the operations which we perform: find x, which returns the representative, that is the root element which contains the x. Union, which merges the set containing x and y. And then make set operation, which creates a new set containing the element x. And initially, look, like for example, element, we are having some elements. Like for example, it is 1, 3, 4, 5. It is something like this connected. And one we are having 6 and 2. So initially, let's say 3 is the root of this one and 2 is the root of this one. So find x. It returns the representative root of the set containing x. So for example, if I'll say find 5, it will give me 3. because 3 is the root of 5. If I say find 6, it will give me 2 because 6 root of 6 is 2. If we say find 1, it will give us 3 because root of 1 is 3. Then merge the set containing x and y. Union operation, it merges the two sets which contains value x and y. We use it in case of equivalence relations in a network topology where the equivalence relation, if a relation is you must have write it in discrete mathematics. Equivalence relation is if the relation is reflexive, symmetric, and transitive. It is called as reflexive. Reflexive is when all the elements of the set are related to itself. Then it is called as reflexive. Symmetric is if A related to B, then B is also related to A. That is, if X element is related to Y element, then Y is also related to X. That means the relation is both ways. And transitive relation is if A element related to B and B is related to C, then it means that A is related to C. So this is called as transitive. So if all these three relations are satisfied, then the relation is called as equivalence relation. So the equivalence relation partitions the elements into disjoint sets, which are also called as equivalence classes. So basic data structure which we uses in this one is the uptrees. Idea that represent each set as a tree. Like I did in this one, these are a tree. Represent each set as a tree. So for the root is representative name of the set. So implementation, we use an array where Si is the parent element of the ith element, and if I is the root Si, then since if I is the root, then Si equals to -1 because it does not have any root. So as we discussed, find and union operations. Find x, it will go towards the root until it finds a root. So it will give you the parent node. Union operation will give you, it will combine two sets x and y. We use here union by rank or size or path compression or time complexity with optimizations to make it to make the performance better. Okay, uh, the inverse Ackermann function is also used. So inverse Ackermann function is denoted as alpha n. It is one of the very slowing growing function of the Ackermann function. So if AMN is the Ackermann function, then alpha n is the smallest number of times you need to apply the inverse of E to reach the number which is less than equals to 1. In practice, we use alpha n as less than equals to 4 for all the reasonable input sizes. So the intuition of this is it grows extremely slow, much slower than log n, log n, etc. So for the practical purposes, we treat it as a constant like less than 4 or 5. So it appears in the disjoint sets because when we are using union by rank or size or the path compression, the amortized time complexity of the operation is big O of alpha n. That is the inverse Ackermann function. And it means nearly constant time. But since it cannot be constant, so it is technically slightly more than the big O of 1. The alpine comes from analyzing the maximum number of times a node can change its parent in the tree. For example, if the value of n is 1 or 2, the value of alpine is 1. If the value of n is 4, the value of alpine is 2. But if you see the values are increasing, like 10 raised to the power 80, the value of alpha n remains less than 5. So the alpha n doesn't, it is very slowly incrementing function. So alpha n is the inverse of very fast growing Ackermann function. It appears in amortized analysis of disjoint set operations, guarantees that find or union are nearly constant time. It improves the performance. And for all the practical input sizes, we take it as less than equals to 5. Now next, we have the comparison table of all the sorting algorithm. What is their best case, worst case, average case time complexity? What is the spaced complexity and is it stable or not? So this is all about the sorting algorithms. We discussed the sorting algorithms, stable, non-stable, comparison based, non-comparison based algorithms, inversions. We discussed bubble sort, insertion sort, selection sort, merge sort, quick sort, heap sort, Reddick sort, bucket sort. So we discussed number of sorting algorithms. We discussed what is the disjoint set, union find operation, and what are the inverse increment functions. So you what you have to do, just go through all these sorting algorithms once and implement all these sorting algorithms in C++. If you have any of the questions, you face any issue, just let me know. Thank you. And then I'll see you in the next week, week 5. Have a nice day.